Hi, it's Professor Adam. Let's talk about buffer solutions. Many biological and chemical processes only occur under specific conditions. Blood, for example, is resistant to changes in pH and is said to be buffered. A buffer is a solution that is resistant to pH change when small quantities of strong acid or base are added. They have two general requirements. There must be two components, one to react with added acid and the other to react with added base. And the second requirement is that the acid and base of the buffer must not react with each other. This requirement that the acid and base not neutralize each other results in the buffer being made from a conjugate acid-base pair such as acetic acid and acetate. This table shows some common laboratory buffers, including the acetic acid acetate system previously shown, which has a useful pH range of 3.7 to 5.8. Others, such as the phenolic acid system, have different pH ranges, and some, such as the phosphate systems, can cover very wide ranges of pH. But how do these buffers work? First, let's consider the acetic acid acetate system. The acetic acid is necessary to consume any excess hydroxide that is added. This reaction has a large K value because the hydroxide base strength is much larger than that of acetate. The acetate anion will react with any excess hydronium ions in a similar manner. The large K value here also means that the hydronium ion is a stronger acid than acetic acid. The pH of a solution can be calculated if the concentrations of the weak acid, the conjugate base, and the Ka of the dissociation are known. So, for our acetic acid acetate system, with the concentration of acetic acid being 0.600 molar and the acetate concentration being 0.450 molar, and the Ka being equal to 1.8 times 10 to the minus 5, we can make use of this to calculate the pH of the solution. First, write out the balanced equation for the acid dissociation and then form an ICE table of the changes in the system. Since we know that the values of Ka, we can calculate for x using our expression. First, fill in the values. Now, since the value of x will be very small compared to either of our concentrations, 0.600 or 0.450, we can simplify the expression. Solving this gives a value for x which can be used to calculate the pH as 10.6. Looking a little closer at our previous example, we find that the hydronium concentration is equal to the concentration of acetic acid over the concentration of the conjugate base acetate times Ka. A more general example where the concentration of H3O+ is equal to the concentration of the acid over the concentration of the conjugate base times Ka. If you remember that the pH is equal to minus log concentration of hydronium, then by taking the negative log of both sides will give us a new expression. Remembering that pH is equal to minus log hydronium concentration and pKa is equal to minus log Ka, then this will allow us to obtain the pH of the buffer solution via a new equation, the Henderson-Hasselbalch equation. Let's check comprehension.